I think I'm going to go ahead and get started. Thank you so much for coming, for joining us, taking some time out of your day so you can hear a little bit about the work that we've been doing in Space Raiders. I'm very excited to introduce you guys to the Space Raiders 2026 IREC Preliminary Design Review. This is our very first ever design review, and like I said, I'm very excited to showcase the work that we've been doing. The purpose of this preliminary design review is to hear some feedback about what we are going to about the designs that we've come up with this year. I will ask that you please hold all your questions until the end, and then we will happily answer them. I would like to give a very special thank you to the Department of Mechanical Engineering. Without them, this could not be possible. And I would like to give an even bigger thank you to the Space Raiders for all of their hard work. And now I would like to introduce all of our team leads this year.
Hello, I am Ishan Nayak. I am the 2025-2026 year Aerostructures team lead.
Parker Rapley, I'm the 2025-2026 Composite Materials and Manufacturing lead.
Hello, I'm Yusra Hassan. I'm a mechanical engineering junior, and I'm the recovery lead for this year.
Hi, I'm Jackson Klesper. I am the payload team lead for this year. I am a senior in mechanical engineering.
Hi, my name is Logan Rawls. I am a sophomore computer engineering student, and I am the avionics team lead.
Hello, my name is Eric Sumstead, and I'm a graduate mechanical engineering at Texas Tech.
Hi, my name is Dylan Neal. I am a sophomore mechanical engineering major, and I am leading propulsion.
Thank you so much. You can take a seat now. A little bit more about Space Raiders. We are the rocketry component of the Raider Aerospace Society, and our goal each year is to build a competition rocket for the International Rocket Engineering Competition. This competition is the largest intercollegiate rocketry competition in the world, and as of yesterday, we have been accepted into the 10K SRAD category. So this year we will be going out to Midland, Texas, where the competition is hosted, and we will be flying a rocket there. This year, there were 186 accepted teams. If you're not familiar with the IREC, each category, there are 9 different categories, and they are each based off of a propulsion type and a altitude goal. This year, we are in the 10K SRAD category, and that means that our altitude goal is 10,000 feet, and that is research and develop motor. Those 2 abbreviations at the bottom are going to be very important to the rest of this presentation. COTS is commercial off the shelf, meaning that we bought this from somebody else, and SRAD is student research and develop, meaning that the students in the Space Raiders have created whatever component that it is. The order of this presentation will go as follows. We will talk about each team from left to right. So we will start with aerostructures, and then we'll talk about our recovery, our payload, avionics, air brakes, and lastly, we will talk about propulsion. As I mentioned, please keep all of your questions until the end, and we will happily answer them. I would like for aerostructures, Ishan and Parker, to join me at the front.
Okay, hello again. I'm Ishan Nayak. I'm the Aerostructures team lead, and we're going to be talking an overview first of the major components that we're considering. First, we have our nose cone. That is the first object or body that makes contact with the air. And we're going to talk a little bit about why we chose a specific shape. We're going to talk about an airframe that we chose, why we chose that, as well as this year our fins and what we're doing. So the main problems that we're concerned with this semester and next semester is making sure the stability of the rocket during flight meets the competition requirements, as well as making sure we don't run into the phenomena of aeroelastic instability known as fin flutter, as well as making sure that we have an accurate flight prediction. And next is auxiliary projects that we're working on the side. First being our integration stand, and also introducing carbon fiber as a material choice for our team this year. And with that comes material testing as well. So in this slide, this is our software simulation that we use called OpenRocket. And what we did during the summer was make a test vehicle revision 1 and determine that we can justify moving up from a 4-inch diameter to a 6-inch diameter airframe for this competition year. So working with propulsion, we were able to determine that we could hit our apogee of 10,000 feet, as well as accurate, as well as have a stable calibers. I believe the minimum for our category is 0.8, and then statically it's 1.5. And so as you can see on the right, 1.8, we're matching, we're good with that. Next, I'd like to talk about stability. So we use our OpenRocket to determine stability, correct? So how that works, it uses these equations on the right. By the user, you input data, and then you're given the center of pressure and the center of gravity. So preliminary in our early vehicle, we've determined that it's stable, but we want to verify this, and that's why I wanted to highlight equations there. So we're going to then, once the vehicle is built, measure everything out, and then determine if the software gave us the correct center of pressure, so that we meet the flight requirements. Next, what we determined so far is our fin geometry. So again, by utilizing OpenRocket, we chose a fin shape that introduces low drag and meets our stability and apogee requirements, as you can see. And this is a very early design, but we're going to iterate and iterate until we get a optimized shape. Next is our airframe. So the airframe, it houses all the components and rocket for other teams to house their projects. So for example, our body tube, we chose a 60-inch length in order to house all the other sub-teams. So it'd have our payload bay, we'd have a payload bay, the avionics bay, and the air brakes situated in one frame. And we chose fiberglass because it's a material that we've known, we've used before in the past, and so we're going with that for the nose cone, the body tube, and the coupler, as well as bulkheads. I'm going to give it up then to Parker to talk a little bit more about our fin choice and why we decided to move towards carbon fiber this year.
Hello, I am Parker Rapley. I'm a senior here at Texas Tech for mechanical engineering, and I am the composite manufacturing and design lead. Basically, this year, one of our main goals and one of my main responsibilities is calculating and profiling our fin flutter for our rocket. They want to see some kind of analysis on how stable our aircraft is in flight. So one thing that's considered with that design is your shear modulus. So one thing about carbon fiber is it is a very strong and inflexible material. Has a very high shear modulus when used correctly. So my job was to come up with a way to calculate that and simulate that in a baseline sense. So my first way that I figured this out, and the rest of the team as well, was coming up with a Python program to calculate our shear modulus. So we wrote a program that goes through and has for each ply of the material, it has a matrix that defines its properties, like our tensile modulus and shear modulus, and then it applies a rotation matrix on this parent ply matrix, and then has a summarization of each individual ply and their material properties to give us our final value. So as you can see over on the right hand of the screen, we have, as our angle increases towards 45, the higher the shear modulus gets. Additionally, you can see on our specific material choice, which is IM7 carbon fiber, after 8 plies of unidirectional weave, we get around, I think it was like 73 gigapascals. Yes. So so on to the manufacturing and testing side of things, we are trying out 2 different methods of manufacturing, one of which is a very traditional method where we do a tip-to-tip layup. This is pretty much just we have a base material, typically fiberglass or a thin plane of carbon fiber that's in the shape of our fins, and then we lay up several layers of carbon fiber onto this. This is a very common way and really easy, quick way to get this done. However, it can be very inconsistent with manufacturing. So we're also going to explore the second method, which is more of a like 4-piece mold, or a negative mold, you could say, where we lay up our 4 plies of carbon fiber in our 45-degree pattern, and then pull a vacuum bag around that and assemble that onto the aircraft. That also allows us to go and test and validate our manufacturing practices and our part quality, and have I guess, more attempts to perfect our process. This will be tested on a 3-inch test vehicle first. This is just a run-of-the-mill, off-the-shelf kit to get more experience and exposure, especially with newer members who are interested in this material, to get them that experience. We will also be doing material testing up to the ASTM D3518 standard. This is an in-plane shear response through tensile testing. So as you can see on the 3rd image, there's a progression of that test. We have the first piece, which is untouched, perfectly uniform, very little voids in the material. And as you go farther to the right, you can see that it deforms quite a bit. And especially in the 45-degree weave, it can unravel when exposed to really high tensile stresses. Well, this will give us a baseline way to calculate our actual material properties on the ground in person.
Hello again. So our auxiliary project that we've been working on is a horizontal integration stand. Purpose of this stand is so that when we're at competition or we're at a test launch, we have a platform that can hold the rocket horizontally. And if somebody wants to manipulate the rocket, you can easily do that. And so at the moment we have everything manufactured and everything able to put together, but we just need to attach the base plates to the chevron brackets. We're thinking of welding those together. And so at the moment, that just needs to be done, and then we have a horizontal competition.
Thank you so much, Ishan. This is the first year that we're going to be pursuing composites, so I hope that this fin can will lead us into many more projects, such as a body tube or a nose cone. I would now like to introduce recovery. So, Yusur, can I please have you up here?
Hello, I'm Yusur. I'm the recovery lead for this year. Okay, so the purpose of recovery is to safely return the rocket to the ground and all of its internal components with as little damage as possible. Traditionally, teams will have a dual deployment system, so they'll have 2 separate parachutes. They'll have one that's called the drogue, and that's essentially a mini parachute, and that deploys at apogee. And then they'll have their second parachute is called the main, and it's a bigger parachute, and that deploys somewhere at a specified altitude that's later calculated. So last year, or 2 years ago, this is the system that we used for Fearless Champion. So we've got the drogue, which is the little pink and black one, and then the main, which is the red and blue one. Per IREC, there's specific rules for the velocities of these 2 parachutes. So for the drogue, the descent rate is 65 to 131 feet per second at apogee. And then the main descent rate is 36 feet per second or 11 meters per second at that specified and it needs to be less than 1,500 feet above ground level deployment. So the purpose of having a main and a drogue is that it stabilizes the rocket during descent, as it gives us 2 different speeds to work at. So we're able to control the landing of the rocket a little better. If the parachute were just to have a main, the rocket tends to drift way further away than we need it to, making recovery a little harder. So taking that main and drogue principle for this year, we're doing the same thing that we did last year, which is called parachute reefing. So parachute reefing is single deploy instead of dual deployment. So the main and the drogue are actually both on one canopy, they're on one parachute. So essentially the drogue, as you can see down in that picture, the drogue is attached to the main canopy, but it's cinched at a certain location on the canopy. So it makes that little mini parachute. And then at around 1,000 feet above ground level, the reefing line that's cinching the drogue is cut through piranha cutters. Piranha cutters are pyrotechnic cutters that are activated through altimeters on the avionics bay. They are activated and then they'll cut the line so that the full canopy is deployed. The purpose of, or the benefit of having just the one canopy is that it reduces the initial shock of having 2 parachutes deploy instead. It also minimizes the packing space on the rocket and the packing mass. And it's better for stabilization, and it minimizes some of the entanglement that can come up from shock cords and shroud lines from having 2 separate parachutes. So this year we'll be making an SRAD elliptical shaped canopy. So parachute reefing occurs in 3 main events. The first event occurs at apogee, so 10,000 feet. You'll have 2 altimeters as part of the avionics bay that will activate black powder charges, and that will separate the nose cone from the body tube so that the drogue can deploy. And then through descent at around 1,000 feet above ground level, event 2 will occur, where the piranha cutters will cut the reefing line of the drogue, and the full canopy will be deployed. And then it'll slow descent until event 3, which is landing. So our biggest calculation for right now was figuring out how big we wanted the parachute to be. Elliptical shape generally has a CD of 1.5, so that's what I based the calculations off of. We went for a velocity of under the canopy of around 8 meters per second, so it needs to be anywhere less than 11 meters per second, so that gives us a little bit of leeway. Our expected recoverable weight for right now is 59 pounds. So then using those parameters and the air density and gravitational acceleration, we calculated that the area of the parachute should be 4.46 meters squared. And then calculating the diameter, we get that the parachute is around 7.8 feet. From previous parachutes that we've made for recovery systems, like last year and 2 years before, a chute of a diameter of 10 feet is ideal. So that's what we are going to go off of this year. We're still developing our manufacturing plan, but we will be using ripstop nylon with windproofing coating for the 10-foot diameter canopy. We're going to use Dyneema line for shroud lines, and we will be using Kevlar cord for our shock cords. And then our gore pattern this year will be the same one that we used last year from Richard Naka, and we'll have around 8 of those around the canopy. And then for testing, we could either take it out on a windy day. We can drop it off of a high building. Last year we actually dropped it off of the USA Arena, so we're hoping we can do that this year again. It was very fun. And we could also put it through load cell testing.
Thank you so much, User. Very excited to see what recovery is going to do this year. And as you said, yeah, I hope we can all drop it off the USA because that was quite fun. I would now like to introduce payload. So Mr. Klusper, if you can join me.
Hello again, everybody. I am Jackson. I am the payload team for this year. You'll have me better? Okay. slide. Of my control. Okay, so payload is the team in which we design, determine, and develop a scientific experiment to go along board with the rocket. Last year, we developed a ham radio repeater that was capable of extending the range of any transmission from the ground. This year, we are planning on making a ionized radiation detector out of a Geiger counter and a Mueller tube. The purpose of doing something like this is to, one, graph that data, and two, be able to give a relative reading dependent on like the height or your apogee. So as you go increase in height, it would show you the increase in radiation point. This is important because as you increase in height, radiation becomes more and more prominent, and we would like to determine at what point radiation becomes hazardous to not only human health, but mechanical and electronical health. So a quick system breakdown. The detection system consists of 3 parts: our ionizing radiation detector, our J305 Geiger Mueller tube, and our ESP32 microcontroller. The radiation detector gives 3 readings: our radiation CPM, so clicks per minute, our equivalent dose, and our radiation pulse count. And a quick explanation of how a Geiger counter Mueller tube works. As ionized gas, so the air around it, enters the tube, any ionized electrons will be pulled towards the glass side panels, and it will be counted by the system, and that count is produced in clicks per minute. So this year, we will be containing our payload in a 2-unit CubeSat. So that will be 100 by 100 by 200 millimeters. It will be printed from 3D PLA plastic. And the purpose of doing a 2-unit CubeSat is, 1, it gives us bonus points at IREC, but also 2, it is a form factor and professional way to house a payload of this size for astronomical purposes.
Thank you so much, Jackson. That was really wonderful. If now Bryce and Logan would like to join me at the front, we're going to talk a little bit about this year's avionics.
Hi, my name is Logan. I am the avionics team lead, and this is our ground station sub-team lead, Bryce. So just to start out, I'd like to give you a little overview. We're going to start out with our COTS recovery electronics, and like Yusher said, that deploys our recovery events and also provides the official record for IREC. And secondly, we'll go over our custom PCB flight computer, which we are hoping to have 12 degrees of freedom sensor suite, where we'll be able to collect all that data, process it through an extended Kalman filter, and use that to control our air brake system. And we also have our Horizon ground station, which is going to be our tracking system and live telemetry and live video system. So just to start out, a little review. COTS recovery is going to persist of 2 main functions, and that's going to be a altimeter and a GPS tracker. Our first is what deploys the recovery devices based on the altitude. At apogee, it will deploy the parachute, and at a specified height, we will be disreefing the parachute through our reefing system. We also use our GPS system to track the rocket throughout the flight, not only for recovery, but for additional data points through the flight. The most important fact about this is that it serves as the official altitude record for IREC. So for the Berryman Award, that is what number we will be basing it off of for our score. Our first device is the Altus Metrum Telemega. It performs both of those actions in a combination. It is a dual altimeter and GPS. It will be paired with its TeleBT ground station, and that will give us not only the tracking and altitude data that we need, but it also measures some additional flight data that we can use to compare to our custom flight computer later on. Our secondary systems as backups are the Featherweight GPS tracker and Blue Raven altimeter. They are well trusted and used through our mentors and our members, and they will be serving as a backup to our telemega just in case. Next, we have our Apex flight computer. This is what is going to be controlling our air brakes and you reading from sensors to allow us to control the air brakes. How will we do that? We will be using JLC PCB's assembly service, which allows us to give very detailed and strict rule-following design files, and in return, they are able to not only print out our PCB and give us solder masks, they will also assemble it for us, which helps with a lot of the inaccuracies that can happen with more consumer soldering. Then, after we get it assembled and delivered, we will do testing on all of our power rails, all of our signals, and all of our data connections. And after that, we will cover all of the devices we're going to put on it. So to start out, we're using a dual-core ESP32 based microcontroller, which will act as the brain for our system, and that will read from all of our sensor suite, process that data, and then send the control signal to the servo. Secondly, we have our RF system. It's going to be a LoRa-based 415 megahertz radio, which will act as the control and tracking data for our Horizon ground station. Next, we have our SD card storage system. It is typically not advised to use an SD card due to vibration on a rocket, but we've chosen a system with a hinged design to help clamp it down to the board and minimize any of those disconnections. Then we have our backup flash memory, which will not only store flight data during the flight, just in case we don't have the room for it on the SD card, it will also store the configuration for these sensors. We then have our onboard 5-volt regulator, which will take our 3S 11-volt battery and step it down to 5 volts to power our telemetry system. And then we have our external servo connections. This year, we're going with an external controller for the servo to act as a UBEC, which will allow us to take that 11 volts again and step it down to the correct voltage for the servo. But it has a little bit of additional components, and that's why we're going with an external commercially tested one. Then for our sensor suite, we have a 6-axis, that's 3 axes of acceleration and 3 axes of gyro sensor. We have a 3-axis magnetometer we're going to pair with that to send through some sensor fusion to allow us to do 3D attitude estimation to give us the orientation of the rocket in free space. Then we have our high G accelerometer. This allows us to capture the peaks of acceleration. While we don't expect to see anything upwards of 16 G, which is the low sensor, we want to be able to cover that full range with the full fidelity. We then have a precision barometer, which allows us to measure altitude within a centimeter level, which will be in the future acting as our altimeter functionality, but it also provides us another data point that we can feed into our air brakes control system. Lastly, we have our GPS module, and that lets us do the tracker functionality of the rocket. To put all this, to house it all, we will put it in a avionics bay, which will be housed in the upper shoulder of the air brakes. And that allows us to, one, have a strong base to lay up against. We're not just in the airframe. It also allows us to be right next to the servo that we are controlling. We're still working on a lot of these devices. You might see a couple empty shelves in there. That's because they go by order of category, what they're doing. We've got the COTS recovery avionics up top, and we've got the RF telemetry board, which is not developed yet since we are still working out our tracking station. Then you've got the custom flight computer below that, and then below that will be our battery management system, allowing us to not only charge our battery, but give us alerts if that ever drops below desired amount. And I'd like to pass it on to my team lead, Bryce.
Good evening, everyone. My name is Bryce Wilborn, and I'm here to talk to you a little bit about our new Horizons ground station. The goal of this ground station is to participate in 2 additional competitions, along with the main one getting to 10K feet. One of them is a data telemetry visualization competition, and the other one is a live video feed competition where we're taking live video from the rocket during its ascent and descent and actually transmitting that live on the ground. After a lot of link budget calculation and analysis, we've decided to go with a 3 link system, starting off with a 915 megahertz high beam width 5-element Yagi antenna. And the goal of this antenna is to help with tracking the rocket from the ground using GPS data, velocity data, gyroscopic data to actually allow our ground station to use servo motors to track the rocket during flight. The second one is a live sensor telemetry link that is going to be around 415 to 430 megahertz. And that's going to have the rest of the sensor data that we're going to be sending down to the ground station for a live telemetry visualization suite software that is currently being developed in a web software. And the last one is an analog video signal that's going to be sent at 2.4 gigahertz in a parabolic dish antenna that will allow us to actually see from the rocket's view the ascent. This is a very simple block diagram of how that's actually going to work on the rocket side. On the left here, you see that we have a RunCam analog camera. That's just the tiny camera that's actually taking a video, probably going to be facing down towards the Earth as it's flying. And that signal will be going into a 2.4 gigahertz, around 2-watt transmitter unit that will turn that signal into a frequency modulated signal that can be understood by antennas. And then from there, we're probably going to be using a 2.4 gigahertz cloverleaf video antenna, which is just a circularly polarized antenna that will be really good signal strength as it rotates as well, because we are not allowed to actually control the rocket's rotation as it flies, and that might actually mess up some of our gain normally. And then on the sensor side of things, we have 12 different sensors that will be taking different data measurements on the rocket during its flight, and all of those will send its data into our Apex flight computer that he mentioned earlier. And from there, we'll be developing another flight computer, the Zenith flight computer, that actually take all of that data and then send it to 2 more links. On the right side, you see the tracking data. That's all the data like the GPS, the velocity, the acceleration, everything we need to actually track the rocket from the ground side. And then all the other telemetry will be sent along this other 450 megahertz coil antenna for us to use simulation software. And this is just a little GIF of what potentially our visualization suite might actually look like. We have a lot of things going on here. I know we have 2 graphs at the top for velocity and orientation. You may recognize in the top left here, we have a sort of 3D model of the rocket, similar to what you might see from like a SpaceX launch. We're actually developing a 3D model that will be very accurate to what the rocket looks like, and that will be what we'll be putting there. We do have a live GPS, kind of like we'd expect from like a Google Earth perspective of where the rocket is. We actually will be able to switch that from this more 3D view to 2D view to actually help our recovery team track where the rocket is once it lands as well. And then on the, I guess just on the general right over there is a live video of the ground, but for when we actually launch with our system in place, it'll be the rocket's point of view being sent down with that analog signal.
Thank you, Logan and Bryce. We are making incredible strides this year with our avionics, and I would like to say that this is the first year that we will have an SRAD flight computer and a tracking ground station. I would like to have Mr. Derek Sumstad join me, and he'll tell you a little bit about air brakes.
Okay, so yeah, like Olivia said, my name is Derek. I'm the air brakes team lead this year. And so the main purpose and reason that we have air brakes on our rocket is that we're, like Olivia had mentioned before, we're in the 10,000 foot category. And the closer that we get to that actual target apogee, the more competition points we get. So our goal is to overshoot that slightly based on our motor design, and then use our air brake to just chop a little bit off the top and hit that as precisely as possible. Now, to do that, we have 3 main design challenges. We have a hardware, software, and simulations challenge that we're going to go through. For the hardware challenge, our main goal was to maximize our external horizontal surface area to get our coefficient of drag as high as possible. And for the software side, we're going to be using PID control in order to accurately hit our 10,000 foot goal. And we're going to be using simulation side in order to tune our PID loop constants. Starting out with the hardware, this 3D printed prototype to show. You guys on the video may not be able to see it very well, but these fins just come out rotationally. And we chose this design mainly because the last year our fins had 2 degrees of freedom because they were sliding on a plane, and it caused jamming issues. So with this design, to have 1 single degree of freedom, it's very simple, and Also, it gives our servo motor a 3-to-1 mechanical advantage, which is very good for overcoming friction. Here's a image of the inside of the air brake, so you can see how it works. There is a central gear spun by the servo motor and the 3-pin mount. And then on the right side, we have kind of shows the housing. So the body tube slips over those shoulders, and then we have through bolts that go through that in order to clamp everything together. For the software and simulation side, we have MATLAB Simulink running to design our PID loop and test out different constants. We're using RocketPy, which is a Python library specifically designed for simulating rocket flights. It has a lot of cool features, like put in the actual coordinates of your launch site, and it will gather in the date, and it will gather climate data and give you an accurate representation of the atmosphere for that time of year, everything like that. So we're going to be using that to simulate flights and then feed that flight data, Mach sensor data into the Simulink to see how our PID loop does. And then also with the software, it's going to be the SRAD flight computer that Logan had mentioned, the purple one, Apex, is going to be what actually houses our PID code for the rocket flight and does all of those calculations. And also, we're going to be using ANSYS Fluent and OpenFOAM in order to do some preliminary drag calculations in order so that we can accurately simulate our rocket in rocket. So for the PID control, this is the equation that we're going to be using to estimate our apogee during flight. I pulled this straight from NASA's website with the, this is their ballistic equations with drag. And basically what I've done is solved equation 1 on there for the coefficient of drag times the characteristic area. So we're just going to have those as one number. And then I plug that into 2, which is the terminal velocity. And then finally plug that into 3 so that we can get our Y max. And the nice part is that it's based on only our negative acceleration and our current velocity, which means that this kind of setup would work for any rocket, really, as long as you have some kind of braking system to use that. That's pretty much it.
Thank you, Derek. This will be our second year having the air brakes on board. Last year, unfortunately, we were not able to deploy, but I know that Mr. Sumsad will get us there. So thank you so much, Derek. I would like to have Bailey and Dylan join me, and they will tell you a little bit about our propulsion this year.
Hi again, my name is Dylan, and I'm the propulsion team lead this year. This is my propellant sub-team lead, Bailey. So first, we're going to start off with an overview of what we're going to be talking about. This year, we're going to look into manufacturing. This is going to involve making motor cases for our rocket motors, making nozzles, also making closures, improving our load transfer for our static fire, and also we're making pouring motors this year. Next, we're modifying propellant this year. We're going to talk about how we're modifying propellant. We're going to talk about why we're modifying the propellant, and we're also going to talk about characterization. Lastly, we're going to talk about testing. That's going to involve the amount of static fires we're doing this year. Bailey, if you would like to take it away.
Okay. Hi, I'm Bailey, the propellant lead. Before we talk about editing the propellant itself, we want to talk about just a little bit of what we experienced last year. So our Formula Blue in general has kind of a slow burn rate. And last year we experienced having issues with our simulation data not matching our experimental data. But we did some characterization tests and got that all taken care of. But this year we want to increase the burn rate and also increase your ISP. So your ISP is your measure of efficiency. And so the way we're going to alter our formula is for our burn rate, we're going to increase the copper oxide. And for the ISP, we're going to decrease the aluminum particle size.
For our copper oxide modifications, the copper oxide itself is the catalyst for the decomposition of ammonium perchlorate. So as you can see, that's our formula over there. It has all of our, I guess, chemical ingredients, if you will, our weight by percentage, and then the function of everything that's over there. So your ammonium perchlorate is your oxidizer. It's also the majority of our propellant formula. And the catalyst for the decomposition of ammonium perchlorate, your copper oxide, will increase your burn rate and also increase your thrust. So we increase the copper oxide percentage by steps. We had found that your copper oxide should lie between 2% and 5%. So we went up by 0.5% and we poured 3 batches of copper oxide. And those are the percentages up there. And we altered this by a scaling factor. So when you increase one chemical, you have to decrease everything else, because there are 3 ratios that you really can't mess with. That's your AP, that's your ratio between all of the micron sizes, your oxidizer to fuel ratio, which affects your combustion temperature, and then your binder to curative ratio, which is just like your binders just bind all your chemicals together, and your curative just like is what makes our propellant a solid instead of a liquid. So yeah, so our scaling factor, we just found that by our new percentage of copper oxide and divided it by the old percentage. And yeah, we apply that to the whole formula. For the aluminum modifications, we found that our original micron size was a bit too big. It was 60 micron, and that was leading to the aluminum not burning all the way through. So we decreased it to 23 microns. So when your aluminum doesn't burn all the way through, it leads to agglomeration, which is that bottom picture over there. That's just like a really zoomed in picture of our propellant, and it's the aluminum like agglomerating. So it just kind of sticks together. And when that happens, up on the other side, there's nozzle slag or propellant slag, and it creates like a tiny little thin shell when it gets, basically when it gets spit out your motor. So yeah, so your aluminum is basically, once it burns all the way through, it will increase your efficiency. So that's kind of why we decrease the particle size. For propellant characterization as a whole, we poured 16 motors. So 7 of those motors were with the decreased aluminum size, and then the other 9 were the copper oxide motors with the 3 batches of the steps that we talked about. The copper oxide motors also have the decreased aluminum particle size. That's going to be, I'm really excited to see what happens with those motors. We also are going to have a data acquisition system. So when we static fire all of these motors, that system will collect all of this really important data that we're going to use and plug into these formulas and get our characterization values. So these help the simulation get us correct values that are close to what we get experimentally. So yeah, we also have a program through MATLAB and Python that will do all of these calculations, because they are very long and very confusing calculations. So yeah.
All right, now we're going to talk about some of the accomplishments our hardware team has had this year. So first of all, we needed to manufacture 54 millimeter hardware to characterize our motors this year. As Bailey mentioned, we're modifying our aluminum and our copper. This is going to involve up to 16 static fires this year. This is a huge step up from last year, where we only did just about 6 fires, and a handful of those went correctly. So this year, our hardware team has gone down to the shop and manufactured 5 nozzles made out of JC3 graphite, a slightly more coarse and less fine graphite than is typical with COTS manufacturing. However, it is cheaper and easier to source. And we found last year that it holds up to the combustion gases and motor temperatures. So we made 5 nozzles ranging from a very small throat diameter to a very large throat diameter. The reason we did this was because having a small throat diameter means that you will have increased pressure in the combustion chamber. And stepping the throat diameters means we can step the pressure of the combustion chamber. We want to do this because we do not know with a certainty how much of a pressure spike we will see in these characterization motors. So we want to start at a large throat diameter and then gradually step our way up to a smaller throat diameter. Next, I'm going to talk about testing. So last year, we had testing equipment that got the job done, but we wanted to see some improvements. As you can see up there, we have a picture of our previous motor coupling. It was a fitting tree with a pressure transducer off to the side and a plug. The fitting tree was attached directly to a Ford closure in the motor, and all of the thrust from the motor was transferred through the fitting tree onto a load cell. Problem with this is we found if fitting tree was for some reason off kilter, it would mess with results. It was also not an ideal design as the motor wasn't the load cell, and the load cell to motor was, the load cell and motor were not coupled together directly, meaning that they could both have a degree of freedom on a planar. So this year we manufactured a motor coupler that is modular. It can fit 98 to 38 millimeter motors. This coupler is a lot more secure than our previous year's coupler. It has multiple diameters to fit the multiple diameter motors that we plan to fire in it. It has a hole through the middle of it to allow a pressure transducer to be attached to the Ford closure so we can read pressure as well as thrust. We also have an improved DAC this year. Last year we had a custom SRAD DAC. It used a Arduino to capture data from the pressure transducer and load cell, which we use for our calculations. This year, we acquired a U6 lab jack, gratefully, our mechanical engineering department financially supported us to purchase a piece of commercial software like that, or hardware. This new data acquisition system has an increased sampling rate up to 25,000 samples per second. It also has a huge amount of possible configurations. You can plug a lot more instruments into this data acquisition system. It's a lot more modular. It also has a higher bit rate than our last data acquisition system. And finally, it has commercial software libraries as well as a ton of support and resources online, meaning we can use just some commercial software to gather our data, or we can write our own custom software in MATLAB or Python to interface with our pressure transducer and load cell to gather our data that we're looking. That is it for me.
Thank you so much, Dylan and Bailey. This is our second year making SRAD motors, and I would like to say that this is only one step in our very large plan. So I'm very excited to see where this is going to be going. Thank you for holding all of your questions till the end. I would like to say a really big thank you to the Space Raiders. I am more than proud of you guys, and I am so honored to be able to call you my team leads. You guys are doing a really wonderful job this year, and I have no doubt that we will do very well at competition. All right, if the team leads will join me, we will begin taking your questions. Just if you're on Teams, you can just raise your hand and then we'll be able to answer your question. Okay. Anyone want to go first? Oh, okay. Owen?
Howdy. I've got 2 or 3 questions. Firstly, to aerostructures about your carbon fiber fins.
All right.
I remember seeing something about printing 3D printed nylon molds to cast them into. Uh, have you factored in porosity of a 3D printed part and how that might be handled in pouring epoxy into it? I worry that you wouldn't be able to remove it from this nylon mold that you've created.
Yes, so on top of the regular surface finish, which typically has very coarse layer lines from the printing process, we'll also be having a layer of release material on top of that, either tape or release wax after post-processing with sanding and everything. I've had experience doing that in the past with other teams. That turned out pretty well.
Okay. My second question is to the air brakes team. The area of the brakes, do you have an idea on how much that is, or how, like just a general idea on what your deceleration is looking like?
Yeah, so it looks like somewhere between 2 and 3 square inches per fit. We actually haven't gotten to CFD simulations quite yet, so we don't know how much our drag is going to be increased by. But based on some CFD from last year, it's probably going to be somewhere 10 and 30%.
Okay. And my second question is, well, I love your mechanism with 1 degree of motion to deploy and undeploy. I feel it might be susceptible to centrifugal force because this rocket is going to be spinning at a rate, or at least I'd assume it would be. Will this be an issue, or have you designed to counter that?
Yeah, so basically the main thing is the holding power of our servo. We're going to be using like a 75 kilogram servo, which is fairly strong. It also already has a 3-to-1 gear ratio. So the fin mass is not going to be, unless the roll rate was so high that the rocket is already screwed, it's not going to forcefully deploy it.
Cool. All right. Those are my questions.
Thank you, Owen. Jericho?
I'll go next. Awesome job. First of all, I mean, like, it's really impressive what you guys have done. So just want to commend you guys for how far you guys have come. I did have a question regarding the fin can though, or the fins, I should say. So I know you were gonna, at least what was presented was a positive, negative, like 45-degree layup. Have you guys considered incorporating maybe like a 0-degree layup? I mean, not all of the forces are going to be, directly tangential to the, plane that you're necessarily manufacturing on. So I wasn't sure if you guys had considered or run any numbers on including either a 0 or like a 90 in that layup. I know 8's not a lot of plies to work with.
Yeah, so one of the main things that we were looking at while doing our simulations was the weave orientation. So we had about 3 other ones, or 2 other ones that we're predominantly looking at. One was quasi-isotropic, which had a 0 all the way through 90 a degree of change through each ply. And that one gave a pretty decent result. However, the shear modulus was still quite low compared to just the 45-45. And with, I think, most of the other ones were about the same, or a very similar result. The material is already super strong, especially in that axis. I don't anticipate any issues with the current loading, especially when it comes down to the ground and impacts the ground. Other than that, all the aerodynamic forces are pretty minimal on that surface.
Yeah, that makes sense. Thank you.
Thank you. Hello, I don't think you're unmuted.
Hey, this is Ed Heap here. I'll go next if no one else has got anything. So great presentation, everyone. I have a question on the air brakes. It looks like you guys have about half of the airframe cut out to make you know, a clearance for those fins to protrude out of. I didn't get to see or appreciate any of the substructure on the inside of that subsystem to perhaps compensate for the, you know, structural weakness in the airframe tube and body that's going to create. Can you elaborate a little bit on? Here we go. Yeah, this probably helps.
Yeah, so basically, there's a cut all the way through the body tube where the air brake is mounted, and then the body tube will slide over the top and bottom shoulders, and then we have through bolts going through the fiberglass body tube. There's 6 on each side, and we've done a carbon fiber tear through analysis, or sorry, fiberglass tear through analysis to determine. So basically, our max tensile load on the rocket body tube is when the parachute first comes out and it kind of yanks on the shock cord. And so I've worked with Ishan to do a tear through analysis of that to make sure that those bolts are not going to shear through the body tube. And then we have 4 inches of overlap between the aluminum and fiberglass. So last year with our 4-inch diameter rocket, that was very stable. It's a fairly tight fit as well. And then for the structural, the rocket doesn't really experience much, if any, bending force. So during thrusting, it's almost all normal force. So the 2 sections of body tube are going to be squeezed together on the air brake. That little aluminum lip is plenty strong for that. There's threaded rods that go through all of the actual air brake. So there's 3 1/4-inch by 20 threaded rods. They're plenty strong, especially with the once everything's clamped together, are handling the force anyway. But does that answer your question?
Absolutely. Thank you.
Joey?
Hey guys, can you hear me?
Yes, we can.
Well, first off, great presentation. You guys are clearly very prepared. Looks great. I had a question about the telemetry stuff. We're looking at, or we're talking about having like a constant stream of telemetry for live tracking and stuff. Are y'all just using like the internal built-in antennas on the like GPS and stuff?
So for most of our systems, they all support external antennas. For the GPS tracking system, as of now, it is internal to the rocket, as there aren't any major metal or carbon fiber sections above us to block our view to the sky. And for the telemetry link, at least for the low link that we will be using for the bootstrapping the tracking system, will be a IPEX connector on top of that module right there. And that will connect to a most likely helical or coil antenna, as Bryce mentioned, and that can be placed anywhere within the rocket after we do some testing.
Okay, so did y'all look into it all doing like external antenna? Because we talked about a little bit about not being able to control the roll rate of the rocket and like keeping an antenna aimed down at the ground station.
Yeah, so the onboard antennas, the big benefit of having a ground side live tracking station is that onboard we don't have to focus on getting as much gain or as little interference as possible. There have been considerations to putting those antennas on the exterior to the rocket, and it would involve just a simple cut through the airframe, as we are already oriented properly within there. Although with a tracking station, it shouldn't be as necessary, and that's why we've chosen more omnidirectional style antennas within the rocket. And as Bryce mentioned, that coil antenna should be a little more resilient against those spinning effects.
Okay, great. I had another question real quick while we're on this slide. Y'all talked a little bit about the SD card and the vibrations being a risk on the rocket. Did y'all do like an actual kind of like risk analysis on like what kind of vibrations it will actually be subjected to?
So since the design is still in the early phase, we haven't had the chance to do vibrational analysis. Last year, that is something we did with our AVBay, testing our fiberglass plates and the devices on them. In terms of vibrations, that is exactly why we went with the hinged design, because as opposed to a push-push or a push-pull SD card system where you're just putting it in from the side and any force in that direction can take the card out, This system you have to physically hinge upwards, push the card into, and then it clamps down onto those pins at the bottom. As for how that actually affects the rocket and if we are planning for that, we will be doing analysis in the future for that. And that is the primary purpose of the secondary flash memory, is that we will have some method through software of checking the validity of the test data or the flight data at maybe apogee or landing. And there is a possibility that we will implement a system that will take the flash memory flight telemetry that can be very vibration resistant unless the solder joints come off, and we can dump that to the SD card once we land. Is that
awesome? Yeah.
Logan, and thank you, Joey. Caleb?
Hi, yeah. On that note of vibrational analysis, I was wondering the same thing for your payload, your Geiger tube. If you've done any analysis on that as well, since that's a bit more of a delicate part compared to just, your SD card slot for your AV bay.
Yeah, so like Logan mentioned, we are still in early development, and it is definitely a plan to test vibrationals. Currently, we have a couple ideas of how we're going to dampen vibrations. But as of right now, we have no sure way of doing it, but it is 100% planned.
All right, just want to see if you guys had a plan for that. Thank you. Your presentation was also really great today.
Thank you. More questions online?
Olivia, can I ask you a question real quick?
Yeah, sure.
Pardon me. Really, you guys, great presentation. Well put together. How? What's the budget on this dude?
Well, that's really good that you ask.
Is it?
We are, as I think historically, not a very well-funded organization, but currently I think our rocket budget in its entirety is going to be something about $4,000 to $5,000, but would greatly appreciate any donations because that would contribute to lots more awesome projects.
Okay. Well, y'all talk to me about that. Maybe we'll come up with something there. And then, what kind of hurdles do you see in manufacturing? Time slips away from us as the semester goes by. Are there any kind of things you see putting a wrinkle in manufacturing?
Yes, absolutely. As if you are not, some of our alumni may not be aware, but recently RAS, our shop that we have about 20 minutes away from here, is under remediation. So our entire manufacturing shop, we no longer have that this semester. And it's projected we will no longer have it next semester either. So that's one hurdle that we are trying to overcome, alongside the fact that a lot of our time down in the shop is limited by labs that are also occurring at the same time. So we can't just go down to the shop and do whatever we want at whatever time. So we'll have to coordinate with their schedules alongside our busy schedules as well. So those are two of the really big hurdles that we've seen so far. And I think going forward, we will continue to face some similar issues.
Okay, thank you.
Thank you. Any more questions?
Do we have a name?
Yes. So I think I might actually have a supplemental slide on here. Hold on.
Or is that a surprise for later? Or do you have to name that when it goes up?
Well, off the screen. Let me give this. Let me show you really quick.
Okay.
Let me just share this screen with you guys. We've been workshopping a lot of names because we have kind of decided our paint job so far. I'm just gonna pull this. Others. Here we go. There we go. All right. Can you guys see that? Here? This one? Are you guys seeing this presentation slide?
Mm-hmm.
Okay. So we're thinking we want to do something West Texas because we're West Texas proud. So we have two names currently. We have West Texas Sunset, which I personally think is a little too long, and Llano Estacado, which, very representative of the region. And we've come up with this paint scheme. It is a fade from a sunset to a starry night, and those silhouettes, the buildings that you see there, when we actually do the paint job, we're hoping to do a silhouette of the bell tower and the Jones and maybe the mechanical engineering building. So yeah, these are the two names we currently have. So I don't know, we might have a vote here soon, then maybe we can really nail it down.
I like the top one.
What did you say the name of the bottom one was?
The Llano Estacado.
I think Texas pronounced that Llano.
That's what I do, because that's how we pronounce it down in Austin, but that's not true.
In Llano it is.
Okay, sweet. Well, if there are no more questions online, I think we are going to close our very first preliminary design review. And I would again like to give, we'll do the in-person question. Again, I would like to give a very huge thank you to the team and for y'all for joining us on this evening, even though it's a little bit late, but we really do appreciate all of your feedback. And I hope to see you guys again for when we do our critical design review, which will be next semester, where we will do an overview of what our final designs are going to look like and our manufacturing plans. Thank you so much.
Good job, team.
Thank you.
Thank you, guys.
Good job, everybody. Thank you.
Nice job. Thanks.